think it's time to go. Let's go.
Hello, and welcome to All Space Considered. All Space Considered is brought to you by the City of Los Angeles Department of Recreation and Parks. And also, we like to thank Griffith Observatory Foundation, our exclusive nonprofit partner. I'm Dr. David Reitzel, your host for All Space Considered, and with me tonight is Bill Gruneberg and Jared Head as well. A round of applause for them. Also joining us via Zoom is Laura May. Laura May is actually off at the Grand Canyon right now. She's hosting night sky festivals there. In fact, the Grand Canyon is still open despite the government shutdown for people to go check out the night skies, and she'll be joining us via Zoom tonight. Anyway, All Space Considered is every third Thursday of each month, and tonight is October 16th, Thursday. And you can follow us on Facebook or Instagram or our own webpage, of course, to get all of the information of what's going on at Griffith Observatory. And don't forget to sign up with Griffith Observatory Foundation, and you can get their newsletter for free. You don't have to be a member, and you can get all the information about what's going on. Tonight, we've got a great show for you. We're going to cover the ZWO astrophotography winners of 2025 to start the show. And then we've got our special guest segment with our special guest, Dr. Jim Bell from Arizona State University. He is the principal investigator for the Mastcam Z instrument that's on the Perseverance rover. And he's on the paper that published about potential signs of life on Mars that was there recently. So we're going to hear about it right from one of the authors and scientists that's on the study. And then we're going to return after that with Jared, who will talk about some out to launch. Starship launched, and then there was also a ham in space. Oh wait, I got that wrong. There's no hams.
Oh, we'll get to the ham.
We'll get to that.
Hold the ham. We'll get on right.
Hold the ham. And then, of course, we've got pretty pictures without Ginger. Ginger Rose couldn't be here with us tonight. She's actually off doing a harp gig. She's a professional harpist. And also will be showing off her astrophotography this weekend, winning an award. So we'll hear about that next month from Ginger directly, what she was doing. Then we're going to talk about some space news from the Division of Planetary Science meeting that happened. So it's a lot of planetary work. More Mars, spectacular Saturn, then rock and roll, whatever that's about. And finally, Venus Vents. And Laura May will join us for some of that. So that's tonight's program, folks. Well, we're going to start with this Astrophotography of the Year award. And Bill, this is some amazing photography that was taken here by folks.
It is. I looked at a lot of it. It's really pretty remarkable. ZWO stands for Zhenwang Optics. It's a company that specializes in making optical instruments for astronomical use, and particularly in imaging. And the pictures are just incredible. How many are we going to look at?
We're going to look at a handful of them, but there were over 1,000 individuals submitted.
Yeah.
Over 5,882 entries were submitted. So we're not going to look at all of those. But here is the winner of the ZWO Young Competition winner. And this was a picture taken by Danielle Borsari, who's only 15 years old. Yeah,
15-year-old took this picture.
Of the Horsehead Nebula and the flame in H-alpha. So a beautiful image in glowing hydrogen gas. So just crazy. And this is the competition. Anyone under 18 could win this award. And here we have the Sir Patrick Moore Prize for Best Newcomer. Who's Sir Patrick Moore, Bill?
Sir Patrick Moore is famous for writing lots and lots of books on astronomy, which I read when I was a kid, so they were way before your time. But they were really fundamental in getting me excited about astronomy, that and my dad building a telescope and various other things, but they were an important part of it, and my just early knowledge about what's going on out there came from that.
He was an English astronomer from England, and our own Patrick So often talks about how motivating and inspiring Sir Patrick Moore was. In fact, he's kind of an early Carl Sagan type figure, so for inspiring folks to want to observe the universe. So this is an inspiring picture of a meteor coming through our sky. That's that glowing trail you're seeing. That's the trail from the little grain of sand that came through our atmosphere, passing right under a galaxy. So a really spectacular image, and very hard to capture that. This is one called Fourth Dimension. And this is the Annie Maunder Open Category winner. And this is sort of some avant-garde work. What's happening here, Bill? Do you know what's going on there?
You know, I actually don't know what's going on here.
Well, it looks, what they've done here is they've layered an image of galaxies. So you can see it looks like a James Webb image in black and white. And then they've mixed in an image of a meteorite pattern. If you slice open a meteorite and etch it, you get what are known as Wittgenstein patterns. And they only appear in objects that cool over millions of years. That iron and nickel has to cool very slowly to form those crystal patterns. On Earth, you can't make those. So this is sort of combining a metallic object and the galaxies that are some of the furthest objects from us in a single image. So very avant-garde.
Did you say Wittgenstein?
Wittgenstein patterns, which it's the German term for them. What's the English term for them? We have David Pinsky here, who's a real meteorite expert with us.
There's no real English term that just turned out that they used his name because he first discovered it.
Yeah. So it's the name of the German that first came up with them. But you can see them, and we have them on display here at Griffith Observatory. If you come to our Edge of Space, you can see the polished pattern on several of our examples that we have here.
And that's right outside those doors.
Yeah, so this picture, I almost skipped it. A shot of the International Space Station flying by the moon. This is really difficult to get in this sort of clarity. That space station is moving very quickly, is not near the moon very long, and to capture it right by the Terminator, this is amazing. And this is in the People and Space category winner by Tom Williams. A gorgeous shot of Comet 12P Pans Brooks taking a final bow. So this is in the Planets, Comets, and Asteroids category winner. And again, folks, just inspiring pictures of comet. Comets are icy objects. As they approach the sun, they give off gases and dust, and those are the tails that you're seeing there coming off of the comet. They don't fly off like a jet engine. It's not like a rocket creating that. It's literally the solar wind, the energy from the sun pushing that tail backwards. So very beautiful stuff. So what do we got going on here, Bill?
This is called Crown of Light. It's an Aurora category winner by Kevin Che, I believe was his name. And I assume it's, I don't know how he particularly got this image, but obviously it was during an amazing aurora.
Yeah, an amazing picture there with the fog down below covering there. I don't know the details of it either, but the Aurora category winner.
It's got to be a time exposure, I'm thinking, right?
Yeah.
Yeah.
And then here we've got the Stars and Nebula category winner, and this is M13. And what's M13, Bill? Is that a...
it's a cluster, right?
It's a globular cluster. All those stars formed together at about the same time, so they're almost all the same age, and they're some of the earliest objects that were formed in our solar system. And this falls under the Stars and Nebula category winner, and this is a tough image to get. You can see that glowing gas that's around M13 too in the background. So, believe it or not, this is a picture of the moon. This is our moon category winner, and as the moon, in a very thin crescent phase, was setting, they took multiple exposures and stacked them on top of one another, and you can see the distortions that our own atmosphere causes. And this was taken by Marcella Julia Pace, and it's called The Trace of Refraction, and just another beautiful moonset image, really.
And that's true color? That's the color of the
I
sky?
believe that is. It happened right after sunset. The moon is such a thin crescent, you can picture the sun was just off to the lower left, and it had just set when this was taken. And now our sun category winner, Laura May, are you out there? Are you with us right now? Hey,
Yes, I am.
Yes, you are. And we can't have a picture of the sun without mentioning Laura May. And this is an active region of the sun's chromosphere, and just a beautiful image. And how hard is it to get a picture like this?
It's very, very hard to get that much detail. In fact, looking at the Daniel K. Inouye images, people it's counterintuitive that you need almost something that can get such little details on something so large. But the sun is very bright, and so these are pictures that are shot in hydrogen alpha. And honestly, the level of detail there for someone who is not at the Daniel K. Inouye Solar Telescope, the largest solar telescope on Earth. It's pretty remarkable to get so much detail. And I encourage people to try and get pictures of the sun over the next year or two before we really head towards solar minimum, and we're not going to have as much to look at.
Yeah, solar minimum can get a little boring, although the sun is never super boring, but still, it's not as exciting as it is now. In the skyscapes category winner, a beautiful arcing Milky Way. Of course, this is a fisheye lens sort of a picture, so you're seeing from the kind of left-hand side all the way arcing from the middle off to the right-hand side, staring down this valley, and a beautiful arcing Milky Way over some aurora colors. So this was called The Ridge by Tom Ray. And then the winner was a Galaxies category winner of the Andromeda core. This is the core of the Andromeda galaxy. And Weitang Liang and Qi Yang, my Chinese isn't so good, and Chuhong Yu won the Astronomy Photographer of the Year in 2025 as the overall winner with this beautiful image of Andromeda showing off the gas and dust down near the center where the central black hole is in Andromeda.
Two things to say about this. One is that the people who granted this, the number one, first prize, there have been so many images over the years taken of Andromeda galaxy. It's not that difficult to get something from it. And they said that everybody wants to show the whole big galaxy with all of its spiral arms and stuff. And these people focused in on that very interesting core and kind of downtown region of the galaxy, and that was one of the things that influenced them. But another thing I want to say is that you have a special connection to the Andromeda galaxy.
Well,
right?
I do. Andromeda was my thesis galaxy, so I did get spectra of red giants in the very, very outer regions, just about as far as you can get from this central shot. I was studying the outer halo, the very sparse regions, and we were trying to figure out how Andromeda got put together. Didn't quite do it in my thesis, but it was the first attempt to do that, and it was the first spectra of individual stars that were gotten. Now, people had gotten some planetary nebulae, which are connected to stars, but in terms of it just being red giants, we were able to do that with Keck, which was pretty fun. Yeah. So, well, tonight we are here to talk about, and we have a very special guest, Jim Bell, to talk about Mars and the Perseverance rover. Jim, are you here with us? Can we? There you are.
Here I am.
There's a little changeover in the theater. Folks at the theater, you'll have to be patient as we change over. The YouTube audience gets a little smoother switch. Well, Jim is the principal investigator of the Mastcam Z instrument that's on Perseverance and is a professor at Arizona State University. And you're decked out for the show tonight with your Mars 2020 rover shirt there. That is the official name of the rover. Perseverance is kind of the nickname of the rover. And you've got in the background picture there a shot of where Perseverance was headed when it was headed off to Mars. Where is that we're seeing? What is that location?
We are in a crater called Jezero Crater, which is about just under 50 kilometers across. A big hole in the ground that has channels where rivers flowed into it, and then a channel out on the other side. But the channel out is at a higher elevation than the channels in, and so we know that crater was a lake. There it is. Nice shot.
Yeah, here's
this is a topography, image of topography. So the blue is lower, and the yellows, greens, and reds and whites are the highest.
Yeah. Now it looks like there's an inflow channel on the left and an outflow channel on the right.
Yep. There's actually two on the left. There's one on the far left. There's one, I guess it would be like around 10 o'clock, and another one around 11:30, and then the outflow channel's around 2 o'clock.
Okay. Yeah. Now,
and the reason we went is right there at the end of one of those outflow, actually both of them, but spectacularly on the western one there's a beautiful delta, like you see at the end of the Mississippi or the Mekong River on Earth. You've got water flowing down from a catchment upstream, carrying sediments, sand, rocks, boulders, in some cases. And then it encounters this shallow body of water, and it gently just drops its sediment as it slows down. Wow. And so this is confirmation that there was a lake, a shallow body of water there. And what you're looking at behind me is a little piece of it, right just to the left of the word clays. There's a little white kind of dot there. That's a little piece of the extended end of the delta, and it's that. That's what it looks like from the ground. Okay. It's called Kodiak. We call it Kodiak Butte. And maybe you can see, if you squint, those just beautiful layers as those sands and muds were deposited episode after episode, maybe storm after storm, flood after flood, and moving that delta forward out into the lake. So that's why we came there, because places like this on the Earth are wonderful environments to preserve evidence of the past habitability and life on our planet. And so we thought, well, maybe on Mars, there's a number of deltas like this that have been found on Mars from the orbiters. This is one of the best preserved and best easily accessible with the landing systems that NASA has. So that's why we went.
Okay, so now we're seeing a picture here of sort of the delta in black and white. Now, how far has Perseverance traveled across this delta? It's been driving across it, taking some measurements, taking samples. How far has it gone?
Well, we landed on sort of the R and crater floor over there out on the plains, and then drove down a little bit towards the bottom of the image, turned around, made some measurements of some interesting geologic context, turned around and came up around the word floor, and like between those two craters above the word floor, and then across the front of the delta, and traversed across the front of it, and then up onto the delta, right about where that big crater is in the delta. And look at the craters around here. This is ancient terrain, right? This isn't a delta that was formed last week or 1,000 years ago. These are billions of years old features, 2-3 billion years old, but they're preserved because the delta sediments got lithified, they got harder to erode, and they're left standing against the easier to erode surroundings. So we went by that crater, which is called Belva crater, and then up into that valley called Neretva Vallis, which is the main channel through which all the water flowed into the lake. And we'll talk about Chayava Falls in a little bit. Kept going up that channel, and we're actually outside of the picture now. We're down about halfway to the bottom, but outside a little bit to the left, exploring the rim. That's the rim of Jezero crater, the curved mountain range that defines the edge of the crater. So we're exploring that terrain now.
Well, very interesting. Now let's talk about a little bit about Perseverance and the camera that's on it. The folks are seeing the shot actually at Chayava Falls there. But you are the principal investigator, which means the scientist in charge of the instrument, leading the team that created the instrument, of the Mastcam Z instrument. And we're seeing the picture there. We'll circle it for our audience. Can you tell us a little bit about this instrument and what it can do?
Yeah, Mastcam Z stands for the camera on the mast that can zoom. So it's basically a pair of zoom lens cameras that are up on the mast. And they're similar in some ways to a set of cameras called Mastcam on the Curiosity rover, which landed back in 2012, is still operating on Mars. And those cameras and these cameras were built by a company in San Diego named Malin Space Science Systems, and we work very closely with the engineers and operations folks there. And the mast cams on Curiosity are fixed focal length. One is wide angle and one is telephoto. And that has to do with just how hard it is to make a zoom lens that you can fit in that compact volume and put on a rocket and shake the heck out of it to land on Mars with vibrations and shocks and temperature swings. All that is very difficult to do, and it turned out not to be possible to do back in 2010, 2009, 2008, when the original Mastcam was being designed. And I was involved with that. I was the deputy PI for science on that camera, and we always thought in our back pockets, gosh, we got to get a zoom lens down there. We want to be able not to just take wide and telephoto, but both wide and both telephoto to get really good stereo, 3D views. That's why there's two eyes of this camera, just like we have two eyes, right? Our brain puts the left and right together using parallax. Our computer software puts the left and right together from Mastcam Z. And the navigation cameras, which are the little cameras just outside the Mastcam Zs, those little round ones there, those are very wide angle navigation cameras to help the rover drivers and other engineers. Yeah, there's a nice shot, a selfie taken with the Watson camera. So we put the rover arm out and did just like you would do with a selfie, just did that. and you can kind of looking down the bore sight there. So behind each of those rectangles is a complex set of optics, focusable, zoomable from about 26 millimeter to 110 millimeter focal length. And then behind that is a filter wheel, so we can image in 8 different filters for each camera. And behind that is a CCD detector, similar to the ones in your cell phone or whatever, with RGB filters on it.
Now, is there a reason the apertures are rectangular like that? Was this just to look cool, or looks like it's wearing sunglasses?
Cool. That's part of it. No, the filters are square, and so the beam going through comes out as a conic, rectangular conic section as it comes out. So there was no, if we made them, we could have made them round. It would have just let more scattered light into the system. So we just chopped it off.
Excellent.
But it does look cool. Yeah.
So now we have some shots here that if Daniel, who's editing our chat, is there moderating our chat, if you could find the Arizona State site that folks can download these Mastcam Z images and put it into the chat for folks to see, that would be great, because I'm going to show some of them. And make sure you get the Arizona State site. It's a superior site to the other one that's out there, let's just say. But these are the sorts of panoramas that can be put together from Mastcam Z. How many individual shots go into a typical panorama like this?
This one looks like probably about 20, 25 or so. It looks like it's 2 tiers, a top tier and a bottom tier. And typically we'll do it elevation, azimuth. We'll make a little, like a square wave pattern. Just try to make it the most efficient use of the alt-az mount. So those many telescope people out there use an alt-az mount. These cameras just use a simple alt-az mount. We can't track the sky like your telescope might be able to do, but we don't need to, because the exposures are so short. There's so much signal there. Mars is a pretty bright place, even though it's 50% farther from the sun. It's still pretty bright.
Yeah, now these are very zoomable. I don't have the ability to do that, but you can zoom in on individual rocks on these images because the resolution is so great.
Yeah,
because this is
each of those 20-something pictures is 1600 by 1200 pixels, each of them.
Yeah.
So you end up with these, hundreds of megabytes and gigabyte size panoramas that are.
Yeah. So you can zoom right into those rover tracks, and you can see the imprint from the ridges on the wheels. It's just the details all there. Now, in addition to these red images that's under Mars light, images are released that are under what's called enhanced. And how are these created? This is not as simple as just Earth light, I believe.
Right. So the previous one was what we call natural color. It's just kind of close to what we would see with our eyes. In fact, the red, green, blue filters on the camera are the same kinds of red, green, blue filters as on your cell phone camera. So when we take that snapshot, we get an image, looks like this, and it's mostly red, right? Look, Mars is the red planet, right? Oxidized iron. The signal in those red pixels is highest, but there's one exposure time that's taking red, green, and blue pixels all at the same time. So the red are the highest, the green are next highest, and the blue are the lowest, because there's not a lot of blue here, right? The oxygen, the iron oxides, the oxidized iron minerals absorb all that blue light. That's why red soils are red on the Earth too, right? It's because of the presence of iron 3+. And so that picture that comes back like this, with the one single exposure time, has very low signal in the blue, higher in the green, highest in the red. But there's plenty of what we call dynamic range. There's plenty of signal there. And so what we do is we take the natural picture and we go, okay, go pick out all the blue pixels, and instead of just showing them as really dark, let's pump them up to capture their full dynamic range of the blue pixels. So we enhance the blue image. And it gets very enhanced because the signal was very low, to bring it comparable to the red. And then we do the same with the green, and it gets enhanced a little bit more. So we end up with a much more blue and a little bit more green picture than reality. But we do this because the differences in color are really subtle. They're really tiny. Many, many shades of red. You know how they say that The Eskimos have 50 different names for snow, 50 different words, right? There's going to be 50 different words for red on Mars when people go live there, just slightly different shades. But we can pick them apart. You can start to see the differences in some of the soils and some of the outcrops here. Big difference in the wheel tracks between the natural color and the enhanced color. Yeah. And that allows us to help do the kind of triage. We're kind of a reconnaissance instrument. We got to figure out where do we want to drive. We got to help figure out where we want to collect those samples. And so the color is one of the pieces of evidence that we use to decide where to go. Of course, the geology, of course, the topography, the safety of the terrain, all those kinds of things factor in. But we really want to enhance that color sometimes and bring out these tiny little details.
Yeah. So now, here's a couple of images from the left side and the right side, and there's actually a little bit of parallax in this. You can see the parallax on the instrument deck of Perseverance itself. Yeah. But you're able to make 3D pictures from these. Folks can download stereograms if you've got the old red and blue glasses and see this picture in a form of 3D.
Yep. You can do this experiment at home. These cameras are only about that far apart, a little farther than our eyes, but in the audience or at home, you can just blink left, right, and you see the screen in front of you or my laptop. I see it looks like it's moving from left to right, and that's just parallax because I'm looking at left eye, left eye. And there's just enough parallax for our brains to say, oh, I'm going to put these together, and you get a three-dimensional image of it. And we do exactly the same with the rover cameras. All of the NASA rovers have had stereo cameras like this on them. Partly it's for redundancy, just in case one breaks, we have a spare, right? But also it's to get that stereo, and then we build three-dimensional models of the terrain, and that enhances the geologic interpretation, enhances the rover driver's ability to drive through terrain, knowing the details of its topography. So we use stereo a lot. Almost every image we've taken with the Mastcam Z on Mars, and there's getting close to 200,000 now, almost everyone is part of a stereo pair.
And this is another panorama that's wrapping around. So this is covering a large, swath of, just like you would with your cell phone, folks, if you did a pan, so you're capturing stuff from, 180 degrees. But that looks like there's a dust or a dune of dust or something, black material crossing on top of these almost plate-like rocks. I mean, this is just a fascinating environment here. But you can see the bigger boulders, those are the suckers you'd want to avoid and not run your wheels over, I'd assume.
If we can, yes.
Yeah,
yes, indeed.
And even sand dunes can be really dangerous. So,
and it's active. The sand is moving. We see the sand grains hopping around. The deck of the rover is more than a meter above the ground, and yet it's got sand all over it. I mean, they hop. The sand grains hop. If you've ever been at the beach on a windy day or on a sand dune, right? It's like don't get too close to the surface because you're going to get hurt. And they hop and they bounce and it's called saltation. They saltate, and some of them make it up on top of the rover. It's really incredible.
That's crazy. Yeah. Now, there was some big news recently, and Perseverance was at the Cheahava Falls location, or the Bright Angel Formation. And Laura May, are you with us here? You were going to take on the questioning here for us about this section.
Absolutely, yeah. Very exciting. Obviously, we had this analysis and a paper that you were on that came out, this very exciting rock. I don't know if we have an image of it to show, that had those little either poppy seeds or leopard spots. And obviously lots of talk about biosignature. How excited are you about this? I know that everyone's always very cautious, but how exciting is this?
It's some of the most exciting stuff that we've found on any Mars mission so far. But to be clear, you're absolutely right. It is not the detection of life on Mars. It is not unambiguous evidence of a biologic signature, right? We were very, very careful to call it what it actually is and what's been defined by astrobiologists for a long time now, a whole class of features called potential biosignatures, right? It is a potential biosignature if it shows some kind of evidence, morphological evidence, geochemical evidence, isotopic, mineralogic, whatever, texture, some kind of evidence that maybe this is related to the chemistry or physical processes of life as we know it on the Earth. But we're not sure, and so it really needs additional study. That's the definition of a potential biosignature. And so we think we've actually got one of those in this rock, in this sample. And there's a nice view of it in the sample tube. Those little things called leopard spots, sometimes on the Earth in Precambrian geology, they call them reduction spots. They almost look like cells, but they're not. They're not cells, but they have a similar kind of rounded shape. There's a boundary between an inside and an outside. And the outside of that rock is kind of reddish. If you go back one, you can see it's kind of reddish tan, oxidized iron 3+, typical reddish Mars kind of material. But the insides of those spots are much more gray to white in color. And when the instruments got down there and measured the chemistry, it's much more reduced iron 2+, not iron 3+. And there are different kinds of sulfate and phosphate minerals that are found in there. And there's been transformations of the minerals from the iron 3+ to the iron 2+ and other kinds of sulfates and phosphates.
Now, when you say 3+ and 2+, that involves the removal of an electron off of it?
Yes.
So,
exactly. And so something has used that energy, right? Something has using that electron as energy. It could be a chemical process. We see chemical processes that do that, chemical weathering on the Earth. Biology also does it on the Earth. Simple single-celled organisms, plenty of them, live inside rock and use that extra available valence electron to harness the energy of that transformation, of that reduction. So there's a lot of similarities between these things and these kinds of reduction spots seen in places where we know, because we've taken the samples back to the lab, they've been studied in infinite detail, we know it was biologically formed. There's also examples of these kinds of spots in non-biologically formed mineral deposits. They're special. They're formed in very high temperature. And one of the things we pointed out in the paper, we brought up this alternate hypothesis, non-biologic, and said, we don't favor that as much because there's no evidence for the high temperature transformation that would be required to do that based on what's on Earth. Now, maybe it's just a special Mars thing and it's unlike Earth. You can't, argue that scientifically, but ultimately it's a strong hypothesis. That's all it is. It's a hypothesis. We put it out there, Laura May, in the paper you mentioned. Not that long ago, less than a month ago or about a month ago. And we're basically inviting the scientific community to throw slings and arrows at it, right? That's what you do. It's what we do as scientists. Well, that's an interesting idea, but did you think about this? So we're expecting a whole range of alternate hypothesis papers, or you guys are silly papers, or whatever, but that's what we want. We want this conversation about this exciting discovery of a potential biosignature to be had out there in the scientific community. And if we're wrong, which show us to be wrong. We're happy to be proven wrong, but we've got a decent hypothesis that is testable. The best way to test it is to bring that sample back to the Earth.
Yeah.
Right? There it is, sitting in that.
And a couple years ago, you and I spoke about the Mars sample return mission. And, obviously there's a lot of talk about this right now, the budget, whether it's going to happen, or what's happening right now with Mars sample return. Is it canceled? Is it? Yeah,
it's kind of in limbo. It's, there's 3 versions of the fiscal year 26 budget out there, the administration's budget, the House and the Senate. They're all different. The congressional budget includes some funding to continue our sample return. The presidential budget does not. We don't have a budget, so it's not clear how we'll proceed. Even in the case where it is funded partially by Congress, it's not all funded. It's going to take many years of sustained funding. It will be the hardest robotic thing that NASA has ever done.
Yeah.
going to Mars, landing another lander nearby, figuring out how to get those samples out, getting them into a capsule, putting them on a rocket, launching a rocket off of Mars, capturing the capsule from that launched rocket, getting it back to Earth, landing it safely.
Yeah.
What could possibly go wrong?
There's just a few things to do there, but to catch some folks up, because maybe a few folks are confused, Perseverance has been going around taking, drilling into rocks, taking samples, making measurements with the instruments that are on board, and as soon as it finds something that's like, wow, this is interesting, we should have this back on Earth to use our labs on Earth to do more analysis, it drills a core. Just like we do here on Earth, you can drill a core of that rock, it seals it up in a tube, and what you're seeing in this picture is those tubes dropped on the surface. It dropped off, what, about a dozen of them or so already?
In tubes.
In tubes, and they wanted to make sure if something went wrong with Perseverance, there'd be some there to recover, so they dropped an initial set. Now it has more on board to be left behind again, and the idea is we're going to go collect those and bring them back to Earth and analyze them here. What do we gain by using Earth labs? Why do that?
Yeah, I mean, if you've ever seen, or even on TV or on the internet or in person, like an isotope mass spectroscopy lab, right? It fills the basement of a building on a university campus, right? I mean, they're sophisticated, they're complex, they're high power, they're finicky, they require tender love and care. And what we've tried to do, what we've successfully done with all of these rovers, is take instruments like that and others, and cameras and other things, and put them into a shoebox, compress them in volume and mass and power, and make them much smaller and robust so they can be shaken by the rocket and all that. And we send them there, and they work great, and they get the best data that's ever been taken on Mars, but it's still, you've had to sacrifice a lot of data quality, of signal to noise, integrity, range of measurements. All that kind of stuff has to be sacrificed in the miniaturization and low powerization process and ruggedization process. So the measurements that can be made in laboratories on the Earth are both much higher fidelity and many more kinds of measurements. There's only 7 kinds of science instruments on our rover. And even Curiosity has another 6 or 7, a few that are unique. But it's a small number compared to the dozens and dozens of kinds of measurements that scientists, geologists, biologists, chemists, physicists, make on any kind of sample on the Earth. So we could determine their absolute age dates through radioactivity. Some of these rocks are volcanic, just like volcanic rocks on the Earth. So their radioactive clocks have been reset by melting. We'll know exactly when that happened, and we can understand the relationship between how many craters are there here on Mars and how old is that terrain. We know that for the Moon because of the Apollo samples, but we don't know it for Mars. We're making our best guess. So we can do the absolute age dating, and then anything related to biology and all the isotopic stuff that's critical to identifying the ingredients of life in early Earth samples, all of that can only be done on the Earth. We just can't do those kind of measurements on that rover.
And we've gotten samples back more recently from asteroids like Bennu, for example. Is there anything specifically that we might have learned, from those samples?
Sure. Absolutely.
Applicable in some capacity.
Absolutely. There's a robust extraterrestrial sample community around the world, and they work with the asteroid samples, lunar samples, other meteorites. And in the case of lunar samples and the Bennu samples and others from Hayabusa, for example, those have to be kept very well contained, not because they're going to contaminate us, but because we are going to contaminate them. Right? Oxygen in Earth's atmosphere will change the chemistry, will oxidize the samples that come from this vacuum of space. The spores floating around even the cleanest lab are going to contaminate any search for biosignatures or organic molecules in those samples. So just the process, the practice of containing extraterrestrial samples, which was sort of started with the Apollo samples, and of course technology has progressed so much farther since the late 60s and 70s. Just going through that process is really good and great experience for ultimately Mars and more lunar samples coming back from the Artemis program eventually. And then also just using these instruments that weren't even imagined when Apollo was flying, or maybe even when the OSIRIS-REx mission was launched. Some of them, new techniques, new technologies, better sensors, better algorithms. All that, takes practice. It takes a community of practitioners who know how to do that stuff. And they're getting not only great practice with the Bennu samples and others, but they're doing amazing science. I mean, that's incredible. That little asteroid is like a sponge, right? So much water, so much organic material, clays. I mean, just absolutely spectacular.
Yeah. So,
is it realistic to think that potentially China may get some samples? There are rumors that China has a separate mission for sample returns. How realistic is this? I know we don't know their plans necessarily.
Yeah, I mean, it's more than rumors. They've announced they're going to do it. And they have attempted to orbit and land on Mars and rove on Mars once, and they've been fully successful in all of that in the one time that they tried.
So do you think they're going to go take our samples, or are they going to bring back their own?
I don't think their intention is to do that. I think they're going to do, what I've seen written is that they're going to do sort of a grab and go, kind of like what Neil and Buzz did in Apollo 11. They didn't go far, they didn't stay long. Grab, stash, and go. And the reality is, scientifically, the first samples to come back, whatever they are, from wherever they are going to massively increase our scientific knowledge of Mars. And so, the samples being collected by Perseverance have great geologic context. So we get the great sample selection between dust and sand, sedimentary rock, igneous rock, etc., atmosphere. We get all that stuff, and we know exactly where they came from and what the environment was like. But somebody who wants to go just grab and go, they're going to make a big impact, and I don't mean that in a bad pun, I mean in a positive way. They're going to make a big impact on science. They are going to be the scientific leaders. Whoever does that first will be the scientific leaders in the study of Mars and the terrestrial planets.
Well, fascinating stuff. So we have some time for some questions in our audience here. Anybody in our audience? Yeah, question here.
How much, the battery power, how much do they have? How long can how long can it last?
Sure. The question was, is there battery power on Perseverance, and how long can it last?
No. You may remember the Pathfinder and Spirit and Opportunity rovers, and those were solar powered, and the sun recharged the battery. And ultimately it was the dust on Mars that covered the solar panels and choked the sun out of the sky that killed those rovers. Curiosity and Perseverance are nuclear powered. They use a very small amount of plutonium, non-weapons grade, science grade plutonium, to create heat as it radioactively decays. The heat creates electricity. The electricity does charge batteries, so it does use batteries, but they're recharged through this nuclear power supply. It's the same technology, actually, that's been used going back to the Voyager missions in the 70s. And so we're not beholden to dust storms and the sun like we were for Spirit, Opportunity, and Mars Pathfinder, Sojourner. So that plutonium has a half-life of 78, 80 years, something like that. So that's not going to be the limiting factor. It'll be something else, a dust storm, a cosmic ray, zap something in electronics. The rover accidentally falls in a pit that wasn't visible as we were driving up to it. Mars always wins. Mars will kill these rovers, just like they've killed every other rover. Mars always wins. And the trick is to stay alive as long as you can, and use these incredible assets, these incredible machines, these avatars of us. That's what they are. They are avatars of us, seeing, walking, touching, smelling the landscape, because we can't go there yet ourselves.
Any other questions in our audience? Yeah, Bill, you got one.
Yes, well, I've got about 11, but I'll
Yeah.
give you one. Let's say we get the samples, we grab them, we bring them home, and we'll look and see what we find. But at the same time, is there something specific that they think they might find that would lead them to a higher, possibility that this was biologically, the origin is biology as opposed to geology?
Yes, absolutely. I mean, there are certain kinds of organic molecules that come in, left-handed and right-handed varieties.
Right.
And life, as we know it on the Earth, uses a certain kind of that chemistry. Certain kinds of isotopes are preferentially created or transferred in chemical reactions by biologic and not geologic processes. So there's a list from our experience on the Earth of what to look for to say, oh, this is a clue, this is a clear clue that this is a biologic process. And even on the Earth, there's many examples of, well, it still could be geologic. There's a big community of Precambrian geologists who are trying to figure out when did life really begin on the Earth, and they're arguing about not seeing the fossils. Fossils are new on the Earth, right? They're not even seeing the soft-bodied organisms. They're looking at like texture and isotope ratios, and down in the weeds of the science. On our own planet, where we have infinite access to the samples and infinite laboratories, right? It's a hard problem. So we're not kidding ourselves. But yeah, long chain organic molecules, certain kinds of isotope ratios. In fact, the Curiosity rover has an isotope mass spectrometer on board, right? It couldn't be carried by Perseverance because of the sampling system that needed to use that space instead. Because Perseverance and Curiosity are the same basic rover. Perseverance is basically spare parts from Curiosity. Yeah. But Curiosity has an isotope mass spectrometer. So every time they drill into the ground and bring some of that sample into the rover, and they don't core it, they drill it, powder it, bring it into the rover, they make a measurement with that instrument that could detect one of those things. I think it's so cool. We're making measurements every so often on Mars that could detect unambiguous evidence of biologic processes. Now, they haven't yet. There are organic molecules that have been found, but they're all potentially meteoritic or geologically formed. There's no slam dunk yet, but it's exciting.
Those would be really ancient anyway, right? So that could there be some degradation over time?
Absolutely, yeah.
So what's coming up next? What are you excited about that Perseverance is going to explore? You said you're exploring the rim. What should we be looking for in the news next, if you can give us any hints?
Well, the crater itself is pretty old, probably somewhere between 3 and 4 billion years old, 3.5 or so. Once we climbed out into the crater, into the highlands, the rugged mountains into which the crater impacted, those are even older rocks. They're the oldest rocks that we've ever explored with a rover in the solar system. And so they go back to a time where we think life might have been forming on the Earth, the oceans were forming on the Earth. There's very little of the Earth left. A few percent, some little pieces of Australia and Canada and Greenland that are that old. Everything else has been plate tectonics destroyed or eroded away. Yeah. So we're driving around what would be the most ancient rocks on our own planet, looking for the evidence of those early processes, both geologic and potentially biologic. And was it a habitable environment? What was the temperature and pressure like? What can we tell about that because of the minerals that were formed? So, there's still a lot of exploration to do there. I personally would be delighted if after we finish our exploration of the rim, if we turned around and went back to the crater, went back to a place like Bright Angel and Chiava Falls. We only got the one sample there. It took many months to tease out the results that were reported, and by then we'd moved on, right? And so I think it's okay to go back if you found something interesting. We do it as field geologists all the time on our planet, but we'll see. It would take a while to get back. The rover has to continue to survive. We have to avoid that sniper that's taking pot shots at us all the time. And the team has to come to a consensus. The team and NASA get to decide where to send the rover. And of course, we take the input from the scientific community, various advocacy groups for science, Mars science around the world, and take all those factors plus the vehicle's health and ability to collect more measurements and all that into account on where we go. But at least for the time being, it's going to be continue exploring these incredibly ancient terrains.
Well, thank you so much for joining us. Oh, yeah, sorry, Lorme, go ahead.
Yeah, I just wanted to ask one last thing regarding, obviously, there's been, so much conversation about human exploration and we're all going to go live on Mars and what, yeah, I see the skeptic brow. What is your thought on the premise that we're soon going to go to Mars and live there?
Well, and it's a good question. Of course, I want to see humans explore Mars. I mean, talk about the hardest thing we will have ever done as a species. I mean, Mars makes Antarctica look like a tropical wonderland, right? And it'll be harsh. It'll be harsh. And, you know, when you get there, there's no oxygen, there's no liquid water. There's not much to do unless you're a geologist. But yet we will go. I believe it. I'm optimistic about that. I know it would be easiest just to go plant a flag, scoop some dirt, and come home. And you know, our colleagues in China are talking about doing just that. And you'd be the first. You'd establish, you know, the leadership, right? It would be harder to go and try to stay and establish a settlement or a base of some kind, like in Antarctica. But that, I think, is probably the better thing to aim for. It'd be great to do that first, of course. You know, of course, I want my nation to lead the world. But being able to stay there and spend quality time in that environment, like geologists out in the field, right? Mapping, sampling, scratching your head, right? Geology is it's forensics. It's CSI Mars, right? What happened here? And so having people out in the field, detectives, scientists and engineers out in the field, I think will be needed to ultimately solve the problem.
Well, fascinating stuff. So let's thank our guests. Thank you, Jim, for joining us tonight.
Thank you. Thanks for
and
having me.
We will have to have you back in person next year. We'll find a time when you're in Los Angeles and all space, and we'll have you here at Griffith Observatory. We'd love to host you. So thank you so much for taking the time to zoom in. So, well, Jared, we've got an out to launch to talk about. And a few things happened out there in space.
Yeah, just a few things this past
A couple
Monday.
of things happened on Monday. So we're going to roll the footage here.
Yeah,
and,
we're talking about sending humans to Mars. One of the vehicles proposed to possibly do that is SpaceX's Starship Super Heavy launch system that they have, and they did their 11th flight test of it, which you can see heading on the uphill here from Starbase in Texas. So down at the tip of Texas as it flies out over the Gulf of Mexico.
Now this is a taller rocket than the Saturn V.
Yeah, it's just about 400 feet tall.
Oh, that's all.
So to give you an idea, the actual Starship, the vehicle that sits on top, is bigger than the stack of the space shuttle combined.
Wow.
So like the whole space shuttle, including the external tank. It's huge. Just a nice shot of the bottom of the Super Heavy booster on its way up. That's 33 of its primary engines, which are called the Raptor. There you get, running at full song right there, just looking beautiful on the way up. Of course, someone like me who does a lot of propulsion work, it's
hard to believe that's real, honestly.
Yeah, it's really cool. Now, Starship Super Heavy does an interesting thing called hot staging, where Starship, the upper stage, actually fires while still attached to Super Heavy, the booster. And then the Super Heavy booster fires its engines still and pulls itself, does I guess I'm going to start calling it a flip and dip, because it flips backwards and then it dips out. So we'll see if that sticks or not. But it continues on into at the moment, a suborbital path to land in the Indian Ocean. However, the Super Heavy booster comes back into the Gulf of, now at present the Gulf of Mexico, but it has returned to actually land back at the launch site, and it has done so successfully. But in this case, this booster flying again, they brought it back over the Gulf of Mexico there and had it hover about 200 meters above the surface of the ocean, and then had it drop in. And this is a view of that as it was coming in, so you can see it's kind of working really hard to balance itself.
Yeah. Well, the accuracy of it, where it's going, they had to be here to take this picture.
Yes.
So it's nailing the accuracy of where it wants to be, it looks like.
Yeah, and then here it comes down into the ocean. And of course, thank you SpaceX for cutting it before we could see the end result.
The X feed didn't have the whole landing. I think you can find it out there on some other sources, though.
Yeah. And then with Starship coming back, we are delighted to get live views now of it on reentry. So, before Starship was actually flying seeing this phase of any spacecraft's flight was basically done through animation or a very long-range infrared camera that would show you a bright dot getting very brighter and then dimming away. But now we're actually seeing the interaction of plasma and other things on atmospheric entry. And I just think that's amazing because that's the actual material of Starship glowing right there. Because it's superheating to nearly 4,000 degrees Fahrenheit. And of course, this was very good for SpaceX because they get to test the tiles, which is a really big question mark for Starship. What kind of tiles are you going to use in order to survive re-entry and come through unscathed? And the whole idea is that they want Starship to be like an airplane. You come back, you check it over, you look at it, you put it on top of a super heavy booster, and then you launch it 30 minutes after it's landed. We'll see if you can end up doing that. I figure if anybody can, SpaceX probably could pull it off. But we'll have to see. I like this view from landing. This camera is on one of the aero surfaces, so that's why it's rocking back and forth as it tries to stabilize itself. And then coming through the clouds, it fires its engine. So it does this, like they call it the belly flop maneuver, where it comes down tail first into the ocean, and then that's it. And you can see that little red dot is a buoy out there that has a camera. That buoy cam right there, and again, accuracy. Like launching it from Texas all the way to the Indian Ocean, close enough for your buoy camera out there. And then this was a drone. They had several drones out there that were actually imaging this. And remember, this is bigger than the space shuttle by like 60 feet. This thing is friggin' huge, gigantic, like a commercial airliner coming down. And then into the clouds, belly flop on the engines. Get to see a little bit of the heat shield there, areas where they remove tiles strategically to see how the structure would handle re-entry if there weren't tiles there, and then that was it. And this also, last time a version 2 Starship is going to fly, so that we're getting upgrades for the next couple of flights.
Now, this looked like maybe the most successful flight they've had to date. Am I wrong in saying that?
I would say that for their version 2 Starship and version 2 booster, this was definitely the most successful that they had. Really, the ultimate goal of a test flight is to get data. And the data that SpaceX has really been lacking was re-entry. How are those tiles handling re-entry, and how is the structure in those areas where the tiles have been removed handling being subjected directly to the forces and the heat loads, the thermal loads that you would have on re-entry. And over the past couple of flights, they have survived through that, so they've actually been able to get that data. And that is the most important thing in a test flight, is data, data, data. So, yeah.
So the non-tile areas actually perform pretty well.
Yeah, first of all, the vehicle made it through, so that's usually a good sign. And this time too, it was noted that those aero surfaces that we saw videos of like breaking apart on re-entry were not doing that on this flight. Now we don't know if that was because of that they had tiles there, or they were like previous flights where there weren't tiles there and things were just going their way with it. We'll have to see on that. But in this case, it looked like it was pretty much the cleanest re-entry we've seen from any Starship vehicle.
So do we know a turnaround time for the next launch? Are they on a fast schedule now?
No turnaround time, because this next one is version 3. This is an upgraded version. The guts of the Super Heavy booster and the Starship upper stage have been changed to optimize manufacturing. Things with tiles have been changed. I actually heard that they were increasing production to the point that they're making one tile every 14 seconds, which is way faster than you could even think of doing with Space Shuttle thermal tiles. This is unbelievable. And the next generation Raptor engine, Raptor 3, is what is going to power this next one. It's going to be an upgraded Raptor, more power coming out of it, and very importantly, a extreme simplification of the plumbing and many of the other moving parts of these engines as well, and
Wow.
that is the critical key. They're speaking of Raptor 3 not as a rocket engine, but a mass-produced rocket engine.
Okay.
So, and that will be the big separator, is if they can make those engines as fast as they are saying
And-
they're going to need to make them to have this fleet of vehicles.
Yeah, and they need to be reliable, because recently we've been seeing the Raptors have been mostly firing out of all those engines.
Yeah.
So hopefully this new version will do the same.
Yeah, and they've also been doing things too on some of these flights. Like a couple flights ago, they ran the booster during landing at basically beyond to the aerodynamic limit and then beyond the limit in order to see what it could actually take, and then find that red line and then kind of define where you want your engineering limits to be at for things like that. So some of those booms that you saw coming back were, I don't want to necessarily say intentional, but it's always good to find out where your red line is before you start doing it operationally.
So there was another launch you were going to cover of this little, well, I was calling it a ham, but that's not the right name of it.
I'm trying to figure out why you're calling it ham.
I don't know. It's something my brain did.
So unless you're talking about the chimpanzee ham.
Well, maybe that's where I thought of it, although this is maybe
So-
even a little bigger than the one Ham flew on.
Yeah.
So what is this we're seeing?
Well, this is a specialized rocket that does what we call vertical takeoff, vertical landing, so VTVL. You can see it's taking off there, and its little legs come inside, and it gets itself nice and aerodynamic as it heads up, and it's testing in Japan to be used in the future, potentially for deliveries, so long distance delivery of payloads to areas of strategic importance and other things. There it is, its little fins, what we call grid fins popping out, basically fins that allow airflow through and you can maneuver them to work with it. This company is also developing a fuel cell system for use on the moon as well. They just announced at IAC, which is sort of our big aerospace conference that happens every year. And there's its little leggies coming out as well. And they just announced that they're going to be doing fuel cells for the moon. So if you are a company that needs it, you can go to this company who's developed this rocket. I don't know if you guys have ever heard of them before. They're called Honda. But yeah, Honda is now in the spaceflight business. So go figure, right? Everybody wants a piece of the space pie. And it was great because Honda just dropped this on everybody. They were like, oh, by the way, we now have a rocket.
By the way.
And then Blue Origin was like, hey, wait a second, we're the ones who tell people after the fact.
This is the Civic Deluxe or something?
Yeah. I was going to say, usually it's a Honda Civic at 3 a.m. in the morning with an exhaust waking everybody up, right?
Yeah.
Now you've got one of these.
I drive a Civic. It's a nice car.
Yeah. There you go. Well,
this is the rocket type, the R type.
the Type R.
The Type R.
Exactly.
Mine's a rocket.
So, Bill, we're going to get you one of these. And we'll have you do a review for us.
Nice.
Well, thank you for that, Jared. Another interesting out to launch this month. Thank you.
The mostest.
The mostest.
The
Yeah,
mostest.
each month we like to feature something that's the mostest. It's a little tongue-in-cheek because, anyway, I always find it interesting, the furthest galaxy, where you're going to keep finding them further and further away. The brightest star, the whatever. So sometimes it doesn't mean so much, but this time we have a mostest, Bill, that is kind of close to your heart. You love these things.
Yeah, when we first started, we've been reporting on fast radio bursts for years because they found the first one, detected the first one some years ago. FRB is short for fast radio burst, and they're a complete mystery. We don't know what is going on that is causing this, but it's just a sudden kind of explosion of energy from some point in space. Pretty much all in radio wavelengths. Radio is a form of light and energy, and again, we don't have any idea what actually causes them. But this is a kind of a giant step forward because they used a special instrument called chime, and let's see, did I put what that actually is? I forget what it actually stands for, but it's a great instrument, and they detected a fast radio burst with chime, but they also have, you can see these 3 outrigger stations. They're slightly smaller chimes spaced really far apart across this continent, and that allowed them to do some triangulation and find very close to where this particular fast radio burst happened. And it's an important one because it is the brightest. It's the most energetic, brightest FRB that we've ever encountered.
Yeah.
And here you can kind of see where it is. That's the distant galaxy, and that little red dot next to the F is where this
where it
happened.
came from, but there's no star associated with
No.
it that we can see clearly.
No.
It might be having to do with a neutron star or a magnetar, maybe a highly
hard to detect,
magnetic object. We're not sure, but this one was about 130 million light years away in this faraway galaxy, and it was this incredibly bright burst of radio waves. So
The
that's
brightest ever, and we went back and forth a little bit because I kept looking at the paper and also articles about, do they mean it's like, is it like magnitude, meaning that's the brightest looking star, but that's just because it's close to us, and another one is much brighter, but it's much farther away. So was that what was going on here? Because this was relatively close. It's in a fairly close, 130 million light years away.
It's pretty close, actually.
It is pretty close, astronomically speaking. So, but I determined for myself, because they talked about FRBs that have been found inside our galaxy, those would, of course, been the brightest ever if they, even brighter than this one if it were just a question of proximity, but it's not. This is actually the most energetic, the biggest, brightest FRB that has ever happened while we've seen. And these things, by the way...
So wait, let me get that clear. I'm a little confused. So this was... Would this look brighter in the sky compared to one in our galaxy, or was this...
No, probably.
Okay, so,
I don't
so this
know
was
that,
dimmer, but it was just an incredibly energetic event.
Yes.
And when we take into account distance, this was the brightest one we'd ever seen. So it's a little bit like you could know that a light bulb was super, super bright, but if you moved it really far away, it would look dimmer than the
I'm
light
also
on your
getting
cell
it's
phone.
not how it looked. It's not the brightest we've seen. It's the brightest that we've ever detected.
That
meaning-
we've detected.
Yeah, that it's actually given off more. And these things produce in like anywhere from a tiny fraction of a second to maybe as long as 3 seconds. They produce, as much energy as the sun does in like 3 days. So it's a lot of energy.
A lot of energy in the
that comes
radios.
out in just no time at all.
Now, it's what we're trying to say is it's the absolute brightness
Yes.
of this. So it's the wattage stamp of it. If you take this object and move it further away, we would have received less signal from it. But it was the brightest radio release of energy that we've seen. So an amazing object. Well, we're going to step through very quickly some of the pretty pictures without Ginger, because we are running a little late, so we need to watch time, everyone. But this is NASA Webb Explorer's the largest star-forming cloud in the Milky Way. This is a near-cam image and a beautiful image for our Halloween time in orange colors.
Orange and black,
So,
and this is in infrared. This is
yeah,
also...
we need to move along on these
Yeah,
bits,
okay,
so
so
just
all
I'm
right.
stepping through them pretty quickly. So this was another NASA Webb image exploring, but it's the MIRI image, so this is the longer wavelength image of it. You can see, you can compare them a little bit zoomed in. Another beautiful image that looks a little bit like maybe a specter or a ghost or a zombie or something with the eyes there for Halloween.
And those eyes are galaxies, not stars.
Yeah, those are galaxies, and they're spiral armed, star-forming regions there around them. And this is about 704 million light years away, a pair of interacting galaxies. Another ghostly image, the ghost of Cassiopeia IC63. This is 550 light years away in the constellation of Cassiopeia. This is an emission nebula, so you're seeing glowing gas.
Oh, this is great.
Yeah, the coldest place in the universe. It's about 5,000 light years from Earth, and this is the Boomerang Nebula, and its temperature is minus 272 degrees Celsius. That's just 1 degree warmer than the coldest temperature you can get, which is known as absolute zero. So a very, very cold location.
Very cold.
A little bit
Take a
warmer
sweater.
than the roof in winter.
Yeah.
Yeah, we're
Now,
working on the roof.
here's our giant black widow for Halloween, 10,000 light years away in the constellation of Circinus.
Circinus.
Circinus?
Circinus.
Circinus,
Yeah.
anyway. Circinus, anyway, that's interesting. I
Yeah.
can't pronounce things well. But it's the Black Widow Nebula. It's hiding in dust. And here it looks like a bat flying at us in the constellation of Ophiuchus. It's a dark nebula with dense material.
Does look like a bat.
And here's the Veil Nebula by David Pinsky, who's
Right
here in the
there.
audience with us.
This
Round
guy.
of applause for David Pinsky.
Nicely done, David.
That is beautiful.
This is the Veil Nebula, and it was taken up in Lockwood Valley, which is the location where the Los Angeles Astronomical Society allows talented astrophotographers like David Pinsky to take beautiful pictures like this. This is about 2,400 light years away in the constellation of Cygnus, and he took it with an 80 millimeter refractor with a modified Canon T3i. So if you want to know the details, incredible talent that Mr. Pinsky has. Yeah, another round of applause for him. This is the Ghost of Cassiopeia, taken by Kareem. How do we say his last name? I'm going to butcher this. I'm sorry, Kareem. El Mahudi. Yeah, another Los Angeles Astronomical Society member. So if you are out there taking some beautiful astrophotography, send it in to us, and we're happy to feature it. This is the Rosette Nebula, and kind of looks like a skull shape a little bit oriented. It's about 5,000 light years away. And then we have the Owl Cluster. You can see the owl that's there.
Of course, of course.
So, of course. And this was taken by Anthony Perkic, another telescope demonstrator here at Griffith Observatory. Well done, Anthony. Our jack-o'-lantern pumpkin sun. So,
evil looking to me.
Who carved that one?
This was taken with the Solar Dynamics Observatory, and it's in high energy. So you're seeing the prominences and the active regions of the sun. Spooky prominence of our sun, taken by Laura May. Laura May, are you still here with us?
Yeah. So this was a prominence a few days ago that hung out for actually about 2-3 days, which is rare. We've got solar rotation obviously happening, and then they do get ejected sometimes when they're that large. But that one's about 8 times the size of the Earth, somewhere around in height, and had a little cloud passing in front of it, mimicking that beautiful prominence. So again, another hydrogen alpha sun.
Yeah. So you're seeing the brightest stuff there, that's the sun, then the cloud blocking the most of it. And in about the 7 o'clock position or so, you can see it looks like there's something sticking off the edge of the sun. That's the prominence. So it's hydrogen gas elevated. Beautiful shot, Laura May.
Very beautiful.
This was a rocket launch that was taken near our Zeiss Dome here in Los Angeles, and another David Pinsky image. So just a beautiful shot. Looks like a comet, but that's a launch from Vandenberg Air Force Base. And we have a moonrise taken by Todd Kunioka, another employee here at Griffith Observatory that's rising over Mount Wilson. So just a beautiful shot of the moon. And finally, we'll end with another shot from Laura May. And this was taken where you currently are. How did you get this?
Absolutely. Yeah, so this was an image I actually took it during I was doing a program, some talks on the moon. And we do these wonderful moonrise events. And honestly, if you've never seen a full moon rising over the Grand Canyon, I urge anyone to go see this, especially right now. We're still in the maximum lunar standstill somewhat. So, where the moon sets and rises goes a little further on its range, and so it's a wonderful time seeing those amazing kind of purpley shadows, and the moon rising, is in these very thin canyon walls. It's absolutely majestic, and I recommend anyone go to the Grand Canyon, enjoy the dark skies there, and get to see a moonrise on a different day than the dark skies. Perhaps.
Now, and you're there for how many more days?
So I'm here for another week or so. I'm still going to be giving some talks, even though we have a shutdown. But we still have some astronomy programs. We're in fact the only programs that are still running, thanks to the Conservancy, because we are not park employees. So come down to the Grand Canyon and see the dark skies there. Yeah,
if you're going to be anywhere near, come on by and check it out. It's a lot of fun. Well, we're going to close tonight's show with some stories from the Division for Planetary Sciences of the American Astronomical Society. It was a meeting up in Spokane, Washington, and it was a joint meeting with the Europlanet Science Congress. So there was a lot of information about, well, frankly, solar system objects. So we're going to jump through some of these here quickly. There were some Mars results. This was taken by the HOPE orbiter. The United Arab Emirates has an orbiter around Mars, and it was analyzing the atmosphere. And you can sort of see the atmosphere is denser in certain regions, and it gets thinner and kind of is bouncing around, going up and down. That's actually a gravity wave. They were studying the gravity wave motions. Different than gravitational waves. Gravity waves are in atmospheres of planets. Don't get it confused with the LIGO stuff. Here's an image of the pole of Mars, and there was a study studying the atmosphere above this pole, and Mars has a polar vortex, a lot like the Earth does, and it's extremely cold, about 40 degrees Celsius colder than the air outside of it. And believe it or not, this allows some ozone to form there. And ozone's normally destroyed in reactions with UV, but in extremely cold temperatures, you can actually have it hang out there a little bit. It freezes away what little water vapor would be there and allows the ozone to accumulate there. And this was taken with the ExoMars Trace Gas Orbiter Atmospheric Chemistry Suite in combination with temperature measurements from Mars Reconnaissance Orbiter. So it was a couple of orbiters working together, a couple of instruments, and they were able to detect that colder region up at the North Pole. And the idea that Mars could have had an ozone layer way back billions of years ago, at that time we were talking with Jim Bell, 3 billion years ago or so, that could have protected that life down there. So the chances that life could be around may be a little higher. The Europeans are sending a rover scheduled for a 2028 launch to Mars's Oxyoplanum, and it's going to go look for evidence of life as well. This is the Rosalind Franklin rover, and chances it might find signs of life have been boosted by a couple of studies. This study showing that large boulders have been falling off the sides of these cliffs and rolling down into the center of the valley and center of the crater, making those boulders easily available for Rosalind Franklin to go measure them. They're between 2 and 8 meters in diameter. In these 4 different ones, you can see the trails leading down into the center. Well, those boulders were buried in the sides of the crater, and that protected them from intense UV radiation and other things that could break down organics. So these boulders, they're going to be able to drive up to them and maybe measure some organics that wouldn't last billions of years if they were on the surface. So they're able to get deeper in. In addition, there's some clay minerals that were brought by floods. Mars had massive floods, it seems, and it brought and transported clay minerals from very far away. So it's sort of like gathering all the evidence in one spot, and you can analyze it right there, and you're analyzing stuff far upstream. So you're able to sort of do a broader sweep without having to drive there. So this is an exciting chance to preserve organic minerals, organic molecules within these clays, and that's what they want to see. Maybe they'll find clues for past life, just like Perseverance has been doing. Now, believe it or not, this is a picture of an aurora on Mars. The left-hand image is a little greener. The 2 images on the left are images taken, and you can pick up a little green glow. The image on the right was taken in the same lighting conditions, or very similar. That bright spot you're seeing in the upper right corner is actually one of Mars's moons passing through the scene. It illuminated the sky a little bit, it illuminated the landscape, and that's similar to the left, but the green's missing. There's less green. So Perseverance actually is an aurora chaser now too. This is an artist rendering of what it might look like if you had giant eyes and you could pick it up. But notice the glow is very even. It's not like the sharp aurora patterns that we have here on Earth. It'd be a much more diffuse glow, and that has to do with the Martian atmosphere. Finally, a story about Saturn. Saturn has a strange hexagon pattern up on its poles, and the James Webb Space Telescope, using a spectrograph, analyzed that top section. The near-infrared spectrograph did a continuous 10-hour observation, and it found some strange stuff. In the right-hand image, you can see what almost looks like dark beads circling that bright region. There's these dark things. Well, that glow is the aurora. That's an aurora there that it's seeing, and on Saturn, and yet there's regions where the aurora isn't glowing as brightly. Well, the left-hand side is about 500 kilometers below, and there's this strange, almost lopsided star-shaped pattern that's there, yet it seems to be connected to those beads that are 500 kilometers higher. And in fact, it's even connected to that hexagon pattern. You can see that it's almost hexagonal on here. It's missing a couple of the arms, though, which is kind of strange. But anyway, we can put the video together of it. This is the aurora, and you can see those dark black regions. They're called dark beads. And then we'll transition to here, and you can see there's features that kind of line up between the two. So something is interacting over those hundreds of kilometers from down low all the way up to the ionosphere of Mars. So this was another study that came out with Webb from this meeting. The Gaia satellite, this was a European mission that measured very precisely the positions of objects in the sky and also the brightness of them over and over and over and over again. And it measured lots of asteroids. And you can take the asteroids and measure their light curves, how they change their brightness. And that's a measurement of the rotation. If you have an oblong object, when its wide side is facing you, you're collecting more light. When the narrow side is facing you, you're collecting less. So you're able to measure the rotation speeds and how they're tumbling. Well, if you plot the diameter of the object versus the period of those rotations, they split into two different kinds. The objects up above are spinners. They're just sort of spinning normally like you'd expect an object to do, like Earth. The ones down below are tumbling. They're tumbling all crazy in three different axes. What happened? Well, it turns out that it's collisions. That asteroids that are in a region where they've had lots of collisions and they've been run into a lot tend to be tumblers. They're heading in all different directions. And that makes sense. You're being hit by things. It sends you tumbling. This is actually a Hubble Space Telescope image of an asteroid that was hit. You can see the debris that flew off of it when it was hit, probably leaving the main object tumbling. This study also said these objects are rubble piles, a lot like the objects we visited, because the tumbling, they had to model it. I'm going to go back. The stuff on the right is the model. The stuff on the left is the data. And they match fairly well. It's not perfect, but they're pretty good. In order to get that match, they had to use rubble piles. And they had to allow the objects themselves to sort of reorient and lose their tumble and sort of go back to spinning normally. That'll happen naturally. But you need to have it be a rubble pile. You can't be a solid object. So this is saying asteroids are probably more commonly rubble piles, which was hypothesized in the past. So interesting results there. Now we're going to end with a story about lava, and we can't talk about lava without Laura May. So Laura May, why don't you take this story?
Yeah, absolutely. So we're going to return to the wonderful world of volcanoes. So I don't know if I'm swiping the slides or if somebody else is doing it.
You can tell me to forward them and I'll get them, but if you have control, go for it.
Oh yeah, if you want to forward. So this is if you want to forward to the next slide, so this is a story that concerns lava tubes. So volcanic eruptions often create these very nice kind of cave-like structures that we call lava tubes. So right here, in fact, this is the Nahuku lava tube in Volcano National Park in Hawaii, and it's about 20 feet high in some places, and it formed about 500 years ago. Next slide, please. And so this is essentially showing you how these structures form, right? So they're created when we have a flowing stream of lava from an eruption, and we get a hard crust that can form basically on the surface due to obviously the contact with colder air, and it insulates the molten lava that flows underneath, and it can keep flowing underneath and create this kind of tunnel structure. And when the eruption ends, we then get lava draining from the tube, and that leaves a hollow tunnel. And sometimes this little last image on the right, on the bottom right, will show that they can collapse in places exactly. And so this, when they do, we get structures like these. So this is a pit crater that was created by an empty lava tube in a region of Mars. And so this was found out by the Mars Reconnaissance Orbiter. So really incredible images. And we also have examples of these skylights on our own moon. So here are some little pictures. It's pretty neat to see. We've got these little almost hole punch through the surface. And again, these are these little skylight features where a lava tube may have collapsed. But until now, we had no real proof that they exist on other bodies. So again, we have Mars and the Moon, and we have the Earth, but it was speculative for the rest of the solar system. Now, of course, the rest of the solar system does have quite a few active bodies. We, of course, have Io, Jupiter's very volcanic moon, but there is also much closer to home, our evil twin, Venus. Ooh. So our neighbor planet has the most volcanoes. We have mapped out about 80,000 volcanoes, but we think there could be up to 1 million volcanoes on the surface.
Now this picture people are seeing right now is a radar map that was made. Yeah. So if anybody's confused, Venus is normally very cloudy and white. Why is it orange? Well, we peered through those clouds with radar to make these measurements.
Yeah. The Magellan mission, in fact, went there they left Earth in 1989, arrived in 1990, and we got these beautiful images showing us the surface of Venus through the radar imager. And right there in that little square region is a very special place. So it's one of the highest volcanoes of Venus. We call it Mont Mons. And it is about 8 kilometers high. That's about 5 miles high. And we made computer-generated 3D models of this. So we did land on Venus a very long time ago, but that is not an image that was captured by the Venera mission. But these are these 3D models that we've been able to make with the Magellan mission. And it shows the summit, and you can actually see some traces of lava flows, in these models. And the Magellan mission has been used. The data continues to be used. We went there over 30 years ago, 35 years ago, and we're still using that data. And so there was some research, very amazing research presented at the DPS where they used all of this data. And they created, so we've got here is a detailed map. Again, this is from 1990, right? An image of Venus's surface. And this is the very data that they used for their work. In fact, last year, there was a paper published in Nature. Nature is, of course, one of the great journals that publishes amazing research. And a different team in Italy, so this was presented by, we've got separate teams in Italy working on this, but if you show the next image, we've got right here on the arrow, we think that these are fresh lava flows that were caught in 1990. Again, this is radar imagery. And now, very excitingly, newer research is looking, or may have found lava tubes. So I do want to clarify this is an image from the moon. We don't have the image exactly that they used. It's not totally published yet. But this is to show you the kind of structures that they were looking like. And these are called pit alignments. And this is a feature on the moon that we think was created by the collapse of a large lava tube in these separate sections. And it's about 30 miles long, the entire thing. So pretty remarkable that we're able to tease this out from, again, data from 35 years ago. And if you show the next slide, we've got we see similar things on Earth and also on Mars. So on top, this is in New Mexico, and we can see again these kind of collapsed pit crater chains with the little skylight, just like we saw on the moon. It looks remarkably similar. And on the very bottom, we see that kind of chain of potential crater skylights that may have collapsed into a lava tube. I don't know if Jim is still here and he wants to give us some thoughts on these, but they're certainly interesting. They're very interesting features.
They're interesting and beautiful, yeah. And you're right. The lava was flowing underground, just like it does on the Earth in places. And these pits might be places where you'd want to put a settlement of some kind, because they're underground, protected from solar radiation, protected from cosmic rays, some of them ultraviolet, and so and that might be warmer. There's a little geothermal gradient down there, so might be looking at future habitats for people in this picture.
Yeah. Fascinating stuff. In fact, on the moon, the rills that you see are collapsed lava tubes, we think. The Hadley Rill that was visited by astronauts. So, well, we're going to open up to some questions here. Do we have any questions from our online audience? Laura May, did you get any past to you, or do you see any questions?
Yes, we did get a lot of questions.
Let's take just a couple.
We
don't have too much time.
Yeah, just a couple. So there was a great question, of course, for Jim. With additional funding, can we spot life on Mars?
Yes.
Yes. Perfect.
But I think it's probably not going to be on Mars. At least in the near term, it's going to be bring those samples back and study them with the much better equipment in the labs on Earth.
Great answer. Yeah.
Yep. We've got a question also. Has the Vera Rubin Observatory confirmed any moons orbiting around distant exoplanets? So this is part of the talks I give at the Grand Canyon. We have not yet found any exomoons. They're so exciting, but they're very, very hard to detect. Obviously, if you know anything about the transits and how we detect exoplanets, it's even harder to spot a moon that would obviously move around potentially your planet and be potentially at a different place, even if we see a repeated transit. And so Vera Rubin also, even though it has had first light, they are still doing some of the tests, I believe, on the active optics. So they have found a lot of little asteroids, tiny little ones, but it's not really going to be, I don't think it has the capacity really to find exomoons. That's going to be for, you know, other missions and tests and all of that data.
Well, good questions from our online audience. Now, one more chance for our in-person audience. Anybody have a final question for us here? We've satisfied everybody, I think. So, well, thank you so much, Jim, for joining us tonight. Thank you, Laura May, for joining us. Appreciate you coming. And thank you to everybody in our audience here that joined us. All Space Considered happens once a month, and next month we have a very special guest. Dr. Bryce Bolin is going to talk about 3I Atlas, the interstellar object that's passing through our solar system, came from another solar system somewhere, just past Mars recently, and we're going to hear about that. Laura May, you're on papers with Dr. Bolin, with Bryce, and we're going to have both of them. Yeah, spoilers.
Yeah,
we're going to have both of them here in person to talk about this. Is it an alien spacecraft? Okay, no, it's not. It's in an interstellar comet, but it's different, and we're going to hear about the actual data they've gotten. So it's going to be exciting. So thank you, everybody. All Space Considered is brought to you by the City of Los Angeles Department of Recreation and Parks and Griffith Observatory. And we always like to thank Griffith Observatory Foundation, our exclusive nonprofit partner. Go to our webpage, follow them, join, and you too can participate in as much programming that we have. So thank you, everybody, and we'll see you next month.
Just a quick question. Nope. Watch this online?
Yeah, you can go to our YouTube channel and check it out there.
It stays there.
It stays there. Yeah.